Let's look at one more example of a measure. And then we'll start talking about some properties of measures. So this example is indisputably the most important measure, and it's called Lebesgue measure. Named after Henri Lebesgue, who by and large developed measure theory in the early 1900s. So Lebesgue measure on R, on the real numbers, the real line, we'll take omega to be R, of course. We'll take the sigma algebra to be the Borel sigma algebra on the real numbers. And we'll define a measure on intervals AB by B minus A. So this is for any A and B in R with A less than B. So this is just the open interval from A to B. If I got the line, I got A, I got B. It's everything between, but not including the endpoints. And B minus A is just the length. So this is just the length of that interval. This is almost the most natural measure one would think of. It's just the length of the interval. And I've only defined it for intervals, but similarly to before, so I sort of waved my hands and said, this uniquely defines a probability measure, this uniquely defines a measure on all of these sets, and I'm going to wave my hands again and say, this uniquely defines a measure on all of these sets. Now, you'll note that this measure is not a probability measure. So before, I didn't really prove it, but it's probably not too hard to see that all of these were probability measures. I sort of claimed that. And it's not too hard to see here. I've got n things. Each of them has probability 1 over n. So the probability of the whole thing is going to be n. Is going to be 1. I'm sorry. Here, maybe it takes a little more work. But so, for example, here in the case of half, I'm going to have a sum of things like this, 2 to the k, or 2 to the n. I'm going to sum those up. And this, probably not too hard to, maybe not too hard to convince yourself, sums up to 1. Here, it's pretty easy to check if as x goes to infinity, this limit is converging to 1 because e to the minus x is going to 0. But here, I have the whole line. So if I divided up the line into a bunch of little intervals and summed up the lengths of each of them, so maybe I took a to be 0, b to be 1, and then I took all the intervals of length 1 like that. I'd be missing some points in between, but we could leave those out and we would still see that the measure of the whole line is infinity. So this is clearly not a probability measure. But this measure is used, in some sense, it replaces the dx in a standard Riemann integral. Instead of dx, you use dm. So sometimes this mu is written as m, and you integrate with respect to Lebesgue measure. I'm not going to say what that means, what integration with respect to a measure means, but this is just to sort of give you a hint of what this measure is good for. So let me now give you some properties of measures. Let's make some more space. All right, so this is a theorem. Here comes a theorem. All right. I think this is our first theorem. Basic properties of measures. So we're going to start on this theorem. We're going to have several properties to talk about. So let omega a mu be a measure space. I didn't say what a measure space is. A measure space is just some set omega with some sigma algebra and some measure on it. So that's a measure space. First property is called monotonicity. And this says if I have two sets, E and F, and E is contained in F, then the measure of E is less or equal to the measure of F. So what's this saying? This is saying if I have some set E and then F contains it, then the measure of E is less or equal to the measure of F. F is the whole thing including E. So this is sort of a natural type of thing. Since our measures are positive, you would expect the measure of this outer part to be non-negative. So when you add that extra part, you're going to get more. Our next property is called subadditivity. And this is a handy property. This is a good one. Simple, but comes in very handy. So if we have some sequence of sets, then the measure of the union of all of them is less or equal to the sum of the measures. So you remember in the definition of a measure, we had countable additivity, in which when these were disjoint, pairwise disjoint sets, then equality held here. This was equal to this. Here, these are just some arbitrary sets. They're not necessarily pairwise disjoint. So what we can still say, though, is that we have an inequality. So, we have a similar sort of picture. I've got my E1, not necessarily contained. Maybe it overlaps. Maybe it contains it. E2, got some other thing over here. I got some other thing, some other thing. So I got all of these sets. And the measure of their union is less or equal to the sum of the measures, which you can see sort of clear since there's some overlap here. So here you're double counting or triple counting some places. Actually, let me stop there and we'll continue looking at the next properties in the next video.